Good morning. My name is Jacopo. I'm a professor in the Department of Nuclear Science and Engineering at MIT, and today I want to discuss the economic potential of the new clean energy technology that could be used to decarbonize every sector of the economy, as well as create resilience in many such sectors. That technology I'm going to refer to as nuclear batteries. But let's start with the bigger picture. There seems to be growing support for nuclear to play an important role in a low-carbon world, certainly in the United States. That support comes from a variety of different sources, from prominent climatologists, which have been publicly advocating for the use of more nuclear energy in the battle against climate change. It has enjoyed bipartisan support. The quotes at the bottom of this slide are from the last administration U.S. Secretary Energy Secretary, Dave Rouillet, and the current one, Jennifer Granholm, one a Republican, one a Democrat. There are very well-known investors and captains of industry like Bill Gates, who have personally invested in new nuclear and also have been advocating for an expansion of nuclear energy, both domestically and abroad. And last but not least, some historically nuclear skeptic organizations, such as the Union of Concerned Scientists, have publicly stated that it's important to keep nuclear in the mix if we are to decarbonize our power sector, and in particular, keep the existing fleet. What goes with that support is, for the first time in many decades, also the support from private capital in the United States. There is robust interest in advanced nuclear reactor technologies. You can see here a map in the United States. There are roughly, at the moment, 70 advanced nuclear projects in North America, between the US and Canada, actually. They're not all equally credible and well-funded, but roughly a dozen of them are, and that's certainly a welcome change from the past, in which the innovation in nuclear technology was dominated by only 2 or 3 well-established companies. Now, you're not expected to be able to read this particular slide, but it shows synoptically the number of initiatives, both legislative initiatives as well as in the regulatory context and at the state level and federal level, to support nuclear energy in the United States over the past few years. All passed with bipartisan support, by the way. So the current business model, or I should say the traditional business model for new nuclear, entails a fairly lengthy testing and licensing process. It typically takes 10 years from the time of conception and conceptual design of a new reactor technology to the time of licensing of that particular technology. It is based on field construction of a very large nuclear power plant, typically gigawatt scale plant. And once that process is completed, typically with an investment of the order of $10 billion or maybe a little bit less, the plant is then connected to the electric grid, and therefore provides what is nowadays a commodity. Once the electrons are on the grid, nobody really cares where they're coming from. This model has been very economically unattractive in the US and Western world, in part also because the companies that have been building these nuclear power plants have lost their ability to do so on schedule and on budget. And so we are facing now with several projects ongoing for almost a decade, in a couple of cases over a decade, that are badly over budget and with cost overruns. Now, I should make an important point here, that is in other areas of the world, particularly in Asia, China, South Korea, India, Russia, and to an extent also the Middle East, this traditional model has actually worked quite well for a number of reasons. The companies are more proficient at building large nuclear power plants and managing large construction sites. And these large-scale nuclear power plants have been delivered in those countries on schedule and on budget. So this is really a Western-centered problem, if you wish. However, because we do live in the United States and we care what this country does, and it does have an influence on what the rest of the world does, I've been advocating that nuclear deployment paradigm should shift, that the traditional model is no longer sustainable. And it should shift to what? It should shift to smaller, more serially manufactured systems. The model that you can see here is, or an analogy, I should say, is jet engines or other machines of similar complexity and size, which are routinely built in factories. They're not built in large sprawling construction sites with thousands of workers. We've been accelerated testing on licensing. I think it's reasonable to expect, given the simplicity and the safety profile of advanced nuclear reactors, that testing and licensing should take half a decade, maybe even less. I'll elaborate a little bit on that later on. And producing also higher added value energy products than electricity for the grid. Again, the opportunity to penetrate markets in which nuclear energy is not viewed as a commodity, but is actually affording a premium, or the products from nuclear energy are afforded a premium, would make nuclear much more attractive than today. Okay, so the idea that the nuclear reactors and nuclear power plants to become smaller is I think well accepted within the Western nuclear community, and these new designs basically entail a reduced number and complexity of the nuclear system structures and components. That in turn is expected to reduce the cost and time for design and engineering, and also dramatically reduce the cost and schedule of the demonstration or first of a kind unit. So just to give you an idea for scales, both in terms of cost and in terms of schedule, a large light water reactor, again, a fairly traditional nuclear power plant, might take order of 10 years. In Asia, they take routinely 5 years, but in the Western world, say 10 years, and or the order of $10 billion, maybe a little bit less per unit. A so-called small modular reactor which is, by the way, down now by a factor of 10 in terms of power output, is now expected to take between, let's say, 3 and 5 years, cost of the order of $1 billion. And then the real wild card could be microreactor, which is where I'm going to focus my remarks for today. And that comes down an additional order of magnitude in power output. So now you're looking at maybe 10 megawatt or thereabout. And definitely with a deployment time of 3 years, in fact, possibly much, much shorter than that, and an investment of the order of $100 million. So the financial risk associated with microreactor and small modular reactors is much, much more tolerable than the traditional large machines. I'm going to introduce here the concept of a nuclear battery. So I just called the very small systems microreactors. Well, what is a nuclear battery? It is a microreactor, and so it's a small nuclear reactor that generates between 1 and 20 megawatt. Nuclear is a heat source, so you get it as heat, but you can, of course, convert it to electricity through a power conversion cycle, for example, an air-breathing gas turbine. It is carbon-free because that's the nature of nuclear energy. They're being designed, machines are being designed to be dry-cooled so that they're not, they don't require basically water for cooling, that allows for these systems to be deployed almost anywhere without the geographic constraint or proximity to rivers, oceans, or even artificial basins. It would be a standardized reactor design, fully built in a factory. You can see the scale there is such that a machine of this size could be truly built in factory and then transported to the site in a container, not entirely standard maybe in size, not necessarily in terms of the functional requirements of the container, but that's the scale that we're talking about. The idea here is to have a essentially plug and play set of connections so that within days to a couple of weeks, the customer would be able to start getting heat and electricity from the time of delivery. Because of economic reasons, the system has to operate semi-autonomously, potentially even entirely autonomously, with remote monitoring, not remote control, but remote monitoring. And the system simplicity and inherent sort of safety margins are such that this can be quite easily accomplished. And there are actually examples of much larger power plants, not nuclear power plants, that are operated autonomously at the moment. The last set of benefits, or the value proposition for these nuclear batteries, that the battery operates between 5 and 10 years without refueling. And once it requires refueling, that refueling is not done on site, but it's done off site. So the battery as a whole, as a piece, is shipped to a centralized facility where it's defueled, refurbished, refuel, and then either sent back to the same site or to another site. So the model that we have in mind here is a fleet model. The implication of this is that there is no on-site storage or handling of radioactive material, and that's a big benefit, certainly for the customers. It also has a very small footprint. If you can see here, the little green rectangle in these two photos has been superimposed on a wind turbine and a solar farm of 10 megawatt nominal capacity. And the green rectangle represents the size, the approximate size of a nuclear battery of the same capacity. Of course, in the case of nuclear, the power or the heat are dispatchable, so with a much higher capacity factor than the alternatives. But the point of this figure here is to show really the compactness and high energy density of this nuclear battery compared to other clean energy technologies. And then last but not least, the Western suppliers seem to be in the lead. So companies like Westinghouse, BWXT, or X-Energy all have active nuclear battery development programs, in part supported by the federal government here in the US. So some examples of nuclear batteries, I already mentioned Westinghouse. You see their design up there with a relative scale. There are companies that are looking at the use of nuclear batteries for powering or propulsion, I should say, of freight ships, for example, core power. In some cases, the vision is that the nuclear battery could be truck transportable, as is shown at the bottom right there. And then the set of applications, or the range of applications, is pretty broad, as I think I'll show in one of the upcoming slides. But it could range as far as space. And in fact, the most recent example, one such nuclear battery or portable microreactor, is a NASA kilopower machine that was designed, constructed, and tested in less than 3 years, and for about $20 million. So very, very inexpensive by by nuclear standards, between 2015 and 2018. So very recently. These are just some examples of the designs that are being developed now. Now, the idea of a nuclear battery is not entirely new. Or at least the idea of a portable nuclear reactor is not entirely new. The US Army operated several portable microreactors back in the 1960s. What has changed since then is the development and maturity of a whole set of new technologies that can be used to basically design and realize a 21st century nuclear battery. So these are things like compact and highly efficient gas turbines, additive manufacturing, advanced nuclear materials, robotics, machine learning, you name it. Many of this happen to be US strength. So again, the appeal of these nuclear batteries, in particular in the US, is to sort of regain technology leadership also in nuclear. And then the other thing that makes this a more compelling case now for the development of nuclear batteries is the very obvious synergies with ongoing US government efforts around nuclear. So both DOE, DOD, and NASA have ongoing programs for the development of advanced nuclear technologies for their respective missions. And there is a lot of overlap and synergies and capacity to basically support also the technical needs and the technology needs for nuclear batteries. Now, all these advanced reactors, the nuclear batteries as well as the ones that I didn't cover, the small modular reactors, have an exceptionally robust safety profile. The three basic nuclear safety functions for any nuclear reactors, which are to rapidly shut down the fission chain reaction in case of an accident, adequately cooling the nuclear fuel during that shutdown, and finally preventing any release of radioactivity into the biosphere, are achieved without the need for any external intervention, whether it be operator or pumps or emergency diesel generators. All of that has been eliminated, and that comes from a combination of inherent safety attributes. This is the choice of materials, coolants, fuels that have very, very robust tolerance for normal conditions. So, for example, a coolant that would not boil, it could be a liquid salt, or a ceramic fuel that can take up to 1800 degrees C without releasing any radioactivity or without failing, high thermal capacity in the core, etc. That plus what we call engineered passive safety systems, which rely on natural circulation, thermosiphoning, gravity, pressure drops, and things of that type, as opposed to active or energized components such as pumps, emergency diesel generators, batteries, etc. So if you combine those two things, the three safety functions are achieved without any external intervention. Why is that important? Well, because accidents like the 3 Mile Island, Chernobyl, and Fukushima are essentially eliminated by design. And the so-called emergency planning zone that every nuclear reactor must have by regulations can be limited to site boundary. What that means is that under the worst case scenario, even if there is an event that damages the plant, the reactor itself, there is no need for the surrounding population to evacuate. And that's important for social acceptance, obviously. These characteristics can greatly accelerate testing and licensing. I already mentioned this particular example, the NASA and Los Alamos kilopower test. Because of that safety profile, they were able to basically fabricate it and test it directly at full scale, which is small, and that's part of the value proposition here, without spending too much money and in only 3 years. So this has been done. It's been done in a different context. This was not a commercial effort, obviously, but that model can be replicated. Now, the last point, or the last shift in the paradigm that I'm advocating for, is higher added value for the nuclear energy products. And that can come from either a strong policy signal that recognizes the non-emitting nature, positive economic impact, and contribution to energy security of nuclear electricity. That certainly would be great. It is possible, I would say, under the current US administration. It's more than possible, maybe even likely. But frankly, it's beyond our control as engineers and scientists. And so I prefer to focus on capturing new markets in which nuclear products could sell at a premium. And in order to do that, we need to use the right technology. And I would argue that nuclear batteries are the right technology. So why is this question of penetrating other markets important? Because only 25% of carbon emissions in the United States and worldwide actually come from electricity production, or I should say the electric grid. 75% come from other sectors, for example, industry, manufacturing, a lot of heat needs there, transportation, obviously, buildings, and even agriculture. So if we're serious about decarbonizing our economy, we need to tackle all those sectors. Some of these sectors can be at least partially electrified, but others cannot from a practical point of view, from a cost point of view. So we need to come up with solutions for all those sectors individually. Now, nuclear batteries can find applications in every sector of the economy, and that's part of their appeal. If for applications that require power, whether they're close to the grid or far from the grid, a co-located nuclear battery could provide the energy that is required by those applications. So I'm thinking desalination plants with reverse osmosis that will require electricity, or flood protection. Those are pumps that will require electricity, or hydrogen electrolyzers to produce hydrogen that might require electricity and heat, or just electricity. Data centers, charging stations, even indoor aquaculture or containerized farming requires electricity and heat. Freight shield propulsion, very, very important market, about 5% of the emissions, and even portable pharmaceutical facilities that could be located anywhere, and they would require energy. For heat, or combined heat and power, many factories and chemical plants require both heat and electricity, sometimes just heat. Big market. District heating in northern latitudes, towns, cities, often do find it attractive to go with district heating, and they are currently burning either oil, diesel fuel, or natural gas with a great amount of emissions associated with it. And so the use of a nuclear battery, co-located nuclear battery there would make a lot of sense. Same goes for microgrids, remote communities, islands, even mining operations. I already mentioned indoor farming, to an extreme, space installations, and certainly military bases could serve as a first example of application of nuclear batteries. Now, to be a little bit more explicit, the co-location of microreactors or nuclear batteries with these end users really eliminate the need for massive and costly, sometimes unreliable infrastructure associated with energy storage, transmission, and distribution. So this really bypasses a lot of the overcapacity that we are deploying now to sort of cope with the expanding scope of the grid, and also the intermittency of some of the energy sources that are becoming more and more important. Now, we did a brief survey of some potential heat applications in the state of Washington, and this was part of a project that I ran with the Pacific Northwest National Lab, and we found that just in the state of Washington, roughly 100, this is only a subset shown here, industrial installations could use several megawatts of heat. And currently they're burning natural gas, and again, they could use nuclear batteries instead, and decarbonize their energy supply. These are a very diverse set of prospective customers. It goes from food processing to university campuses to paperboard mills and other factories. So what are the cost targets for all these markets? Well, for heat, the main competition is indeed natural gas-fired boilers. So natural gas boilers are too small for carbon capture and sequestration, so burning natural gas will incur a carbon tax in a carbon-constrained world. So what we did, we looked at the cost of heat generated by or supplied by natural gas boilers as a function of natural gas price. The cost of heat here does not include the cost of the boiler, so it's conservative assumption, if you wish. And we also looked at the effect of the carbon tax, if you wish, on the cost of heat. So the results are shown there. And to make a long story short, the cost target is between $20 and $50 per megawatt hour. That's megawatt hour thermal, or if you prefer better units for heat, would be $615 per million BTU. So if you can hit that target, then you're going to be competitive with natural gas boilers in a carbon-constrained world. Similar idea for electricity. The most likely competition going forward continues to be natural gas generators. And here is shown the levelized cost of electricity in dollars per megawatt hour as a function of the natural gas price. And also as a function of the carbon tax between $0 and $100 per ton of CO2. And it's shown for a natural gas combined cycle that would be grid connected or distributed generation. And again, here, the target can be easily identified from these plots, and it's of the order of 70 to 115. We estimate it's of the order of 70 to $115 per megawatt hour. So if your nuclear battery can hit that target, then there is going to be a market. All right, so what we did next was a levelized cost of electricity and levelized cost of heat analysis. So here are the assumptions, which I'm not going to read entirely, but the hypothesis here is that a nuclear battery is shipped to the site with a fuel core, operated continuously for several years, and then shipped back to a central facility for that refueling and refurbishment. So the nominal size that we pick is 10 megawatt electric, and we need to make some assumptions about thermal efficiency, refueling interval. These are sort of baseline numbers, and then I'll show in the next slides will be the sensitivity analysis around this. But so you have to pick the capacity factor, the refueling and servicing downtime, make some assumptions about the fuel enrichment, the discharge burnup, prices of uranium and things of that type, as well as number of FTEs, number of staff that are required to operate the nuclear battery. Very important assumptions about capital cost, economic lifetime, et cetera, et cetera. So then you calculate the LCOE and the LCOH. The only difference between these two is at denominator you have electric power or thermal power. There's a factor of 3 because that's the thermal efficiency that we assumed. So the LCOE and the LCOH at the numerator have the annualized fuel, operation and maintenance, and capital cost. And for the baseline case results, we get an LCOE of about $85 per megawatt hour and an LCOH of $30 per megawatt thermal. Both are well within that those target ranges that I just discussed a few minutes ago. Now, of course, these calculations have enormous uncertainties, so it's very, very important to look at to do a parametric study, sensitivity analysis, to see how the changes in assumptions change the results. So we vary the parameters one at a time. The first is the power output of the single reactor from 1 to 20 megawatt. That's a big range. Fuel enrichment between 5 and 20%, discharge burnup, which is, for those of you who are not nuclear engineers, so the majority here is a measure of the energy generated per unit, the total energy generated per unit mass of fuel. Now, fuel enrichment, discharge burnup are not technically independent parameters from each other, but here, just to establish, if you wish, a design envelope, we decided to treat them independently. Refueling interval between 3 and 10 years. The nuclear battery fabrication cost, excluding the fuel, between $1,000 and $10,000 per kilowatt. Number of FTEs for operation and maintenance between 2 and 15, and discount rate between 2 and 15%. Capacity factor between 50 and 98%. And obviously 50% would be a site that does not require heat or electricity on a continuous basis. Whereas 98% is one that requires it all the time. That capacity factor obviously does not include the downtime required to ship the nuclear battery back to the central facility for the refueling and refurbishment. So that's accounted separately, but it's accounted for in the LCOE, just not in capacity factor. So the next few slides are show the results of the sensitivity study. I'm not going to go into this in great detail, but basically for each parameter, we looked at the breakdown of the total levelized cost in capital, O&M, and fuel. And if you add those three up, you get the top curve, which is the total levelized cost. And so very briefly here, not surprisingly, the electric power output has a strong effect on the total levelized cost of electricity. The larger power benefits the LCOE and vice versa at the lower power. So economy of scale applies also to microreactors. Everything else being the same, you want to obviously generate more power, and your economics is going to look better that way. So effect of other parameters, enrichment on the left, not surprisingly, higher enrichment, the cost goes up, the total cost goes up, higher fuel burnup, the total cost comes down, and the only cost component that is affected is the fuel cost. The refueling interval, we found that between 5 and 10 years, there is very little effect on the total cost, and going beyond 10 years does not make much of a difference. So there are other considerations that might drive someone to a refueling interval which is greater than 10 years. But from a strictly LCOE point of view, we don't see big differences there. The effect of capital cost is potentially the most important, and not surprisingly, if you go from $3,000 per kilowatt to $10,000 per kilowatt, that's fabrication cost, makes a big difference as expected. Now, $3,000 per kilowatt for a 10 megawatt machine is equivalent to $30 million, and that's actually fairly reasonable. We did a bottom-up estimate of the cost of a nuclear battery, making some assumptions on design, of course, and we found that it was well within $30 million. Just to give you a term of comparison, a large jet engine, which you can think of it as a small power plant generating 50 megawatt of mechanical power, peak takeoff, cost about $25 million, and that's the equivalent of $500 per kilowatt. So different technology, but roughly same physical size, same level of complexity, and generating even more power cost less than what we estimated there, much less. So we think that $3,000 per kilowatt is actually a good baseline. Number of FTEs also not unexpectedly affects the operation and maintenance cost, not dramatically, but significantly. And we have parallel studies showing that 5, which translates to roughly 1 person on site 24/7, is actually quite reasonable in terms of satisfying all the requirements, technical requirements that the operation of a nuclear battery must satisfy. And then discount rate here, again, not surprising. If the discount rate goes up, the total levelized cost of electricity goes up primarily because of capital. Last but not least, also this trend is very obvious, capacity factor. These are high capital assets, so if you operate them at full power all the time, you're going to get a lower cost than if you operate them in a partial load. Now, the last thing we did, we wanted to see the combined effects of some of these parameters. So there are many different microreactor and nuclear battery designs out there, and some appear to be obviously expensive. And why is that? Well, if, for example, you go with a very low electric power, 2 megawatt, you have some kind of new fuel that costs more than the traditional, say, UO2, uranium dioxide fuel, with a decent burnup, but you require multiple people 24/7 on site to operate the machine, maybe translated to 15 FTEs, with a fabrication cost which is over twice as high as our baseline, a little bit higher enrichment, and maybe even long refueling intervals. You can see that the levelized cost of electricity goes up very rapidly. So blue is our baseline case, and orange is our nominal expensive microreactor. And in particular, operation and maintenance becomes high because of the high FTEs and the lower electric output. The fuel more than doubles, and the capex also doubles as expected. So overall, this can become, can go from being $80 per megawatt hour to $300+ per megawatt hour, which incredibly would still be competitive in some niche applications like remote communities, etc. But clearly, you want to be at closer to blue than orange here. So in summary, takeaway messages here are that portable microreactors, also known as nuclear batteries, have the potential to provide on-demand, carbon-free, potential economically resilient and safe energy for distributed heat and electricity applications in virtually every sector of the economy. The cost targets for these nuclear batteries in these large markets are $70 to $115 per megawatt hour for electricity, $20 to $50 per megawatt hour for heat. And it appears that the MBEs have the potential to meet these cost targets if the power output is maximized within the constraints of a nuclear battery. So it has to be track transportable, it has to be passively decaying, passively safe. And the staff ought to be between 0.5 and 1.5 FT per megawatt. That's the range that appears to be tolerable. Low enrichment and relatively high burnup, that certainly helps. Fabrication cost less than 5,000, excluding the fuel, which seems feasible. That is also, I think, a strong requirement, and discount rate less than 10%. We did not find any cost incentive for very long refueling intervals. Okay, I'm going to leave you with this slide here. The top image shows a very large nuclear power plant site in France. This is all quite traditional, beautiful machines. They work very reliably. But as I said at the beginning, they cost a lot of money to build. They take a lot of time to build, and they're fairly inflexible in a sense that they are grid connected. So all you get is just grid connected electricity. So maybe the future for nuclear looks also like what is shown here, the bottom right, much smaller machines, more flexible, easy to deploy, and more suitable for applications beyond the grid. So with that, I'm going to thank you and be able to take questions during the Q&A.